Hello, everybody. In this video, we're going to be talking about how astronomers navigate the stars. How do we locate objects in the sky? And we're going to talk about two different systems. They're going to be introduced in two different videos. And each video is also going to have a tutorial where I use sky simulation software to show you what these coordinate systems really look like if you could project them on our sky if you were to go outside at night. So these are some pretty important concepts that we're going to be covering. They can be a little bit difficult, especially whenever I get to the equatorial coordinate systems in the next video. So make sure that you watch these, make sure that you understand them. Please post if you have questions in a Canvas discussion. All right, so introducing the two coordinate systems, how astronomers navigate and locate objects in the sky, are horizontal and equatorial coordinate systems. This video will focus on the horizontal coordinate system. But I want to introduce both of them. So let's imagine we're outside, we're looking at this fantastic view of the Milky Way, not quite what it would look like naked eye, since this is a long exposure photograph with a foreground put over it. But let's say that you're this person right here, and we're going to go join that wonderful astronomer, and they are going to tell us where the Lagoon Nebula is, which is this red splotch right here with a yellow arrow pointing to it. So how could that information be communicated to you? We essentially have two different choices. We have what I'll call the look over there, point in what direction and how high up. So, hey, look, it's over there. Which this is going to turn out to be the horizontal coordinate system that works for local skies. So in this case, it might be, to give it a little bit more specific than, hey, look over there, it's look south and up 30 degrees. Or perhaps there's nobody there and you're reading an article online and you want to go see the Lagoon Nebula, or say you want to go see Comet Ison, or not Comet Ison, Comet Neowise while I was gracing our skies about a month ago. You'd look up, let's say Saturday, so a specific time, go and look due south and up 30 degrees, or some information like that. For Comet Neowise, I might have told you when it was an evening sky object, go out at 10 p.m., look just north of northwest and up about 15 degrees, and that is where you will find Comet Neowise. So it's basically just pointing out in the sky. So this person might say, hey, it's due south, and point up 30 degrees, and you'll see the Lagoon Nebula. Pretty direct. And this is a summary of the horizontal coordinate system. The more complicated, yet the universal coordinate system is, let's make a globe out of the sky. So let's imagine the entire night sky as this giant sphere that envelops the Earth. And let's put the stars on the inside of that sphere that surrounds the Earth, and then give each different star its own address. So we could do a coordinate system, which will be our equatorial coordinate system of it lives at an address. It lives at some point on the night sky, and then you just need to know how to read the map and go outside and find that coordinate on the night sky. Ask yourself questions like, is that coordinate up at night for this time of year? And given that, where would it be in the sky? A harder one to use, but it is very, very powerful because every object, every star and every galaxy and every other deep sky object has a very specific address, and it doesn't change, and it can be communicated to anyone, anywhere, as long as you know how to translate that. My example here is I put an XY grid on here, just a grid. You can think of these as streets in a city, and you just want to know where on this coordinate grid is the Lagoon Nebula. So you might say, okay, in the X direction, it's at 1, 2 1/4, so 2 1/2 or 2 1/4, and then you go up 1, 2, 3, 4 1/4. So it's at 2 1/4 and 4 1/4, 2 1/4 X, 4 1/4 Y, or something like that. And now you've isolated where that object is. And notice that every object in here has its own unique space in this grid. That's going to be the next video. Let's focus on our local sky, the easier one, the look over there. What direction and how high up? This is really how we communicate in the local sky. If I'm doing astrophotography, this is the coordinate system that I'm going to use. This is, if I'm going outside and looking at the sky, this is what we live and experience from here on Earth. So it's easier. but let's orient ourselves to, if you go outside and look around, let's give some sort of waypoints for us. Some of these terms are going to be new. Some of them are going to be exactly what you think they are, like horizon. So whenever I say horizon, it's literally talking about your horizon. If you picture yourself on a beach, oh, that'd be so nice right now. You have where the ocean divides the sky. You're looking at the horizon, that line that divides the sky from the earth. You're out in the plains in the west, then it's pretty flat, and you have a flat horizon, and it's that line that divides the sky from the earth. A little bit more complicated here since we're hilly and things like that. So in general, you just want to think of the horizon as what is straight ahead. So if you look straight ahead out to the distance, and that would define your horizon, which spins all the way around. So you have your horizon, the line that splits the sky from the earth. Represented here in this bubble, you have the ground, and then here's our horizon right here. A new term for you is zenith, which is really just a fancy way or an official way to refer to the point in the local sky directly above your head. So if I look straight up and point, I am pointing at my zenith, the point directly overhead. It's what lives directly over your head. So for this person, the zenith is directly over their head. And now we're equipped to cleave the sky into an eastern half and a western half, which is going to be a very useful thing, especially since things rise in the east, set in the west, spend half their time on the eastern half of the sky and half their time in the western half of the sky. So what is that midpoint? What cleaves the sky in half into the eastern and western half? It's called the celestial meridian. And we usually just refer to this as the meridian. And the way that you can locate it is you look due north. And for this video, if I point directly at the screen, that's due north. And then you go up through your zenith point, and then you go down to due south. So you have this line that goes from due north up through the zenith to due south, making an eastern part of the sky and a western part of the sky. All right, so now we have some terminology that we can use when we refer to the local sky. What about this coordinate system? What's called the horizontal coordinate system. Notice that horizon is right in horizontal because we are using the horizon, our local horizon. This is the coordinate system that works for our local horizon. The horizontal coordinates are called altitude and azimuth, or alt-az for short. Alt for altitude, az for azimuth. So we have the two coordinates, altitude and azimuth, that make up the horizontal coordinate system. Let's start with azimuth. Azimuth is just spinning around and around and around. So spinning around azimuth. And altitude is how far up. So azimuth, how far around. Altitude, how far up in the sky. Okay, so in azimuth, we're going to describe how many degrees we are away from north. So if I point due north, again, pointing directly at the screen, I'll define that as due north. And then as I rotate to the east, is how many degrees am I away from north? So to go to east, I'd rotate 90 degrees. So east is at azimuth 90. South would be azimuth 180. West would be azimuth 270. And then you can spin back to north. And you could do that for every single degree and every fraction of a degree. It's just how many degrees have you spun around, spinning to the east from north. Not that bad, just how far do you spin around. Altitude also measured in degrees. We define looking straight ahead towards your horizon at 0 altitude. You're not pointing up at all, you're just pointing straight out. And then you can point to straight up 90 degrees to your zenith. So your zenith has an altitude of 90 degrees. Your horizon has an altitude of 0 degrees. And you can point from 0 to straight up. So altitude only goes from 0 to 90 degrees. Let me give you a practical example. So here I have, let's go with the moon that I have right up here. And I'll actually do a stop share for this one. So I have this moon that I have on my bookshelf over here. If I define north as directly towards the screen, I'm going to spin around 90 degrees to the east, and then it's about another 45 degrees. So 135 degrees of azimuth So spinning around 135 degrees this way. And then I have to point upwards. So I'm pointing up. It's not quite 45. Let's call it 40 degrees. So what would the local coordinates, the altitude azimuth, the horizontal coordinates for that be? It would be azimuth 135, altitude 40. And notice I could point to anything in that room using those coordinates. Fairly simple and fairly direct to use. That's why people really enjoy using this one. It's so easy to talk about. Except it has some problems. It only works for right here, right now. Because here we are, we'll take a space view of looking down the Earth, and we'll see lots of diagrams like this, or if you're going through my lecture, so it's good for me to orient you towards that. But we can take a space view of Earth, looking down at the North Pole. So that's what the NP means. And the Earth would be rotating counterclockwise if you're looking down the North Pole. Remember, east is the direction the planet rotates in, so east points that way, which would mean west would be that way. North would be towards me out of the screen, and south would be into the screen from my perspective here. So I'll draw a green line. That would be my local horizon on Earth. Remember, if you're actually on the Earth, you're tiny compared to the Earth. So on the scale of the football field, you're an atom sitting on top of a grain of salt. So basically, you just draw a straight line for your local horizon. You can't see around the Earth. The Earth is giant for us. So this green line is our horizon. Go to the point directly over your head. You'll go to zenith, and you go from north up to zenith, and then back down to south. So this would be our celestial meridian in this perspective. And then we could go ahead and point like, oh, we could figure out how many degrees away from the horizon the star is, say 50 degrees. And let's just imagine that's due east. So that would have, we could do alt S. The problem is the Earth is always rotating, right? Once every 24 hours. So let me go ahead and put the dome on there just so you can get an idea of what this would look like in sort of a 3D perspective, or as best as I can do with a 2D screen. And now let me show you the problem that you could probably reason out with the horizontal coordinate system. The Earth is always spinning. If you watch the sun, it's moving through the sky. If it's moving through the sky, it's moving around from east towards west, and it's changing its altitude in the sky. So it's constantly changing its coordinates. Same for the stars whenever they rise and they set. Same for the moon whenever it rises and it sets. So the horizontal coordinate system it changes constantly. It only works for a very specified time. We also discussed in a previous video that if you go to the southern hemisphere, you have a different sky. So how high things up, if they're actually up in the sky, depends on your location on Earth, your altitude on Earth. So not only does it depend on a specific time, the alt-az system, but it depends on a specific place. So our horizontal coordinate system is only useful for right here or right now, or right here and right now, or specified time in the future, and very specified altitude and azimuth for that time. Like, hey, you wanted to go see Neowise a month ago? Go out at 10 p.m., look just north of northwest and up 15 degrees, look near the Big Dipper, about 2 fists below that, and that's how I was finding comet Neowise. And really what I was using was our horizontal coordinate system. I had a time and a location, how far around and how far up and down I'm going to look. So to give that a perspective from the Earth-based view, from our perspective, and this is kind of what makes it so difficult to start translating between these coordinate systems and really understand, is we live here on Earth and we don't feel the Earth really spinning around. It looks like everything is rotating around us. So you can see here the sun will be rising, changing its altitude and its azimuth as it moves around, and same with the stars. So what we'd really like, instead of having something where every star is moving, changing its altitude and azimuth all the time, what we'd like is a coordinate system where we can fix and say, hey, this star right here lives at this address in space, in the space that we observe, in this sphere of stars that surrounds the Earth that we call the celestial sphere. And for that, that's going to be the equatorial coordinates, which is going to be our next video. All right, if you have any questions about the horizontal coordinate system, go outside and start pointing at some things, use a compass, or post in the Canvas discussions. And also wait, I will be showing using a night sky simulator software called Stellarium what these coordinate systems look like. All right, thanks for tuning in.